All right, at the end of the last video, we left off with this example. This example states, what is the moment of inertia of this object about an axis through its center? The length of the rod is 3 meters, and the mass of each piece is 5 kilograms. So we are going to apply the fact that inertia is the sum over all the masses, mi times ri squared. So mi is the mass of each individual object, and ri is the radius from the axis of rotation to wherever the object is. So in this case, we have two masses. So the inertia is going to be basically m1 r1 squared plus m2 r2 squared. Each of the radii and masses are equal, and the radius is measured from the axis of rotation. So since the length of the entire rod is 3 meters, it's 1.5 meters radius for each end. So we get 5 times 1.5 squared plus 5 times 1.5 squared. And that gives us 22.5 kilograms meter squared. And that's option B. Okay. Also, go ahead and pause the lecture and answer the next video lecture quiz on Canvas. So there should be a corresponding problem to this. Just make sure that you are plugging in the appropriate numbers given in that problem. So here's another poll question. I'd like you to pause the video and think through this yourself first and come up with a response. All right, so at this point, hopefully you've come up with a response. What we're doing here is comparing two spheres. They have the same mass and the same radius. Sphere A is hollow. So sphere A, basically all the mass is concentrated on the boundary and it's hollow inside. And then let's draw this out. So here's sphere A, and we can show that the mass is all concentrated basically to shell. And then we have sphere B, which is the same size, but sphere B is a solid sphere, and the mass is uniformly distributed. And we were asked which one would have a larger moment of inertia. So some of you actually may already be familiar with the different moment of inertia of different types of geometries and objects, but without thinking about those formulas, let's think about the definition or the expression for moment of inertia. Basically, we are integrating r squared over each tiny piece of infinitesimal mass that makes up the entire object. And if we're summing up r squared dm along all the infinitesimal masses, all the mass is concentrated on the edge for sphere A. So the radii are all going to be capital R. Now for sphere B, you have some mass at that same radius, at the same edge, but then you have also mass that is concentrated closer to the center of the sphere. So if we're finding the axis or the moment of inertia about the center of mass, which is directly in the middle of each of these, the r squared dm terms all have a capital R squared for sphere A, and for sphere B, some of them are going to be the full radius, and then the other terms are going to be some smaller radius as you sum up all the masses. So when the mass is concentrated, more of the mass is concentrated further out from the axis of rotation, you have a larger moment of inertia. So in this case, sphere A would have a larger moment of inertia about the axis of rotation through the center. All right, so in this class, you're going to be asked to calculate the moment of inertia two ways. One is you're given a discrete set of masses, and you find it by summing mr squared for each of those. Another is you may be given one of these objects with a uniform density and asked to use these given expressions for each of these shapes. So for example, if you have a thin rod and you're finding the moment of inertia through its center, it's 1/12 ml squared. For a cylinder or a disk, it's 1/2 mr squared, and then you have other common results here. Okay. Oh, and to show and confirm that our hypothesis in the previous question was in fact correct, we said that the shell has a higher moment of inertia than a solid sphere. So let's compare. Here's our shell, and here's our solid sphere. Note that 2/5 is less than 2/3, and the solid sphere does in fact have a lower moment of inertia for the same mass and the same radius. All right, now let's apply the concept of total kinetic energy. So a few slides ago, we talked about calculating rotational kinetic energy by doing 1/2 I omega squared. But what if the object isn't just rotating? It's both rotating and translating linearly. Well, then we end up having two contributions to our kinetic energy term. The first contribution is from the translational motion of the center of mass, and then the second term is from the object rotating about some axis. So let's consider a solid sphere here, and this sphere is rolling without slipping, and the mass of the sphere is 3 kilograms. It's rolling down an incline with a speed of 5 meters per second. So its center of mass is translating and moving with a speed of 5 meters per second. The rotational speed is 3 radians per second. So omega at this instant is 3 radians per second. And we're being asked to calculate the total kinetic energy of the sphere at this instant. So now we're going to be revisiting this concept one more time, but basically for a no slip condition, when something is rolling without slipping, we know that the velocity of the center of mass is equal to omega times r, where this capital R is the radius of that object. So this is a condition we'll revisit, but for this problem, we're going to go ahead and use it and calculate the total kinetic energy. So the total kinetic energy is going to be 1/2 mass times VCM squared plus 1/2. Now I is the moment of inertia of whatever geometry this is, and since this is a solid sphere, we'll go ahead and use I for a sphere, solid sphere, is equal to 2/5 mr squared. Okay, so let's plug that in. 1/2 times 2/5 mr squared times omega squared. All right, so let's simplify things a bit. So the total kinetic energy is equal to 1/2 mv center of mass squared plus 1/5 m. So now for r, we need to figure out what the radius of this thing is. Well, since we know both omega and we know the center of mass, and also note that this would be given in the problem to you. This sphere is rolling without slipping. And for this condition, we know VCM to be omega r. Well, then we can say that the radius is actually just velocity of the center of mass divided by the rotational speed of this object. So we can replace radius squared with V center of mass squared over omega squared times omega squared. And notice that the omega squared cancels out. So we're left with that the total rotational kinetic energy is 1/2 mv center of mass squared plus 1/5 mv center of mass squared. This is a very interesting and insightful expression because it basically tells us that the contribution from the translation of kinetic energy is 1/2 mv squared, and then the contribution from the rotational kinetic energy, which can be written in terms of VCM, is 1/5 mass times VCM squared. So you could uh, you can basically read off what percentage of the energy is in the translational kinetic energy and what percentage is in the rotational kinetic energy. In this case, we're just asked to calculate the total. So we'll go ahead and plug that in. So we have 1/2. Well, let's factor out m times VCM squared. So the mass is 3 kilograms. Velocity of the center of mass is 5 meters per second squared. And then we have 1/2 plus 1/5. All right. So we get 3 times 25 times 1/2 plus 1/5 should give us 7/10. 7/10. Apologies here. Let's write this a little neater. Okay, there we go. Oops. So simplifying all of that, we get 3 times 25 times 7 divided by 10. 52.5 joules. Alrighty. Okay, here's a whole question for you to think about. So pause the video, come up with a response. Once you've done that, we can talk about it together. We have a uniform disk of mass M, capital M, and radius capital R, has a string wrapped around it and connected to a smaller mass M. When the mass M has fallen a height h, what is the relationship between the linear speed of the smaller mass and the angular speed of the larger mass? So as the string is unraveling, this is essentially the same as the rolling without slipping condition, but this happens to be on a basically the disk is spinning on an axle here rather than a sphere or a disk rolling down a hill or a sphere or disk rolling on flat ground. So essentially, we know that if we track some point on this sphere, so as this thing travels down some height h, that's exactly the same amount of arc length that is covered. Basically, that's the same arc length of string that is unraveled from up here. So this arc length is equal to how far in the y direction this mass is traveling. So basically, the linear velocity of this mass corresponds to, so S can be written as big R theta, where theta is what angle, by what angle this disk has moved. And then if we take the time derivative of that, we basically get that ds dt is equal to, so r is staying constant times d theta dt. And ds dt is equal to this velocity. So velocity is just equal to r times omega. And there's a bit of a typo in these responses. All these r's should be capital R's for these options. So that matches with v equals r omega with option B here. Okay, now we have the same situation. We have the mass capital M, radius capital R, and then once this mass little m has fallen by height h, which of the following equations holds true? So just looking at these expressions, hopefully you're thinking some sort of conservation of energy. So go ahead and pause the video and think about applying the concept of conservation of energy to this mass starting here and then moving down some height h and ending up somewhere here, and comparing this initial spot to this final spot and the energies of the two configurations. Okay, so hopefully you've come up with an answer at this point. So when we first start at the initial point, this mass is at rest, the disk is at rest. So the only type of energy we have is, so energy initial total is equal to energy final total. And initially we just have potential energy. Then when we once the mass little m has fallen by a height of h, it's moving at some velocity. So we're going to have some translational kinetic energy of little mass m, 1/2 mv squared. And then for the big mass, it's hinged. So it's not translating in any direction. It's just rotating. And since it's rotating, it's got some rotational kinetic energy of 1/2 I omega squared. And I, the moment of inertia for a disk, as you can go back to your table of objects with their moment of inertia, is equal to 1/2 mr squared. So plus 1/2, so I omega squared with I plugged in, a half times a half gives us a quarter, mr squared omega squared. So we get 1/2 mr squared omega squared. But as you might notice, all the options are given in terms of v squared. So we need to use our relationship pretty much from the last slide, v equals omega r. So since we know v is equal to omega r, we know omega is equal to v over r. So for omega squared, we can plug in v squared over r squared. So 1/2 mgh is equal to 1/2 mv squared plus 1/2 mr squared times v squared over r squared. And then these two r squareds cancel out. Essentially, our conservation of energy statement is the following. Oh, and this was a 1/4, so I accidentally wrote a half there, but notice that with I plugged in, the moment of inertia plugged in, the 1/2 I omega squared goes to 1/4. So this should have been a 1/4, so 1/4 mv squared. And that matches with option B. Okay, we're almost through to the end of this video. The next concept we're talking about is center of mass. So here you see a ball is thrown and it follows a parabolic trajectory here, as we might expect from projectile motion. And this ball is essentially a point mass-like object. Now, let's say we take some large complicated object like this odd wooden shape that we have here, and then we throw this thing similar to the ball. Well, the object itself, notice here, is rotating as it goes through this trajectory. But if you track this one single point all along its trajectory, it actually also follows that same parabolic trajectory. Basically, as if all of its mass were concentrated at that point, it's following pretty much the same trajectory as a point mass. So the punchline here is observations indicate that even if an object rotates, or several parts of a system of an object, of the object's more relative, so indicate that even if an object rotates, or several parts of a system of the objects move relative to one another, there is one point that moves in the same path that a particle would move if subjected to the same net force. This point is our special point called the center of mass, and often we use the abbreviation CM for center of mass. So this special point that is following the same trajectory like the ball is our point of the center of mass of that complicated object. Now, how do we find center of mass? we use these wonderful formulas. They look kind of scary, but when you apply them to a specific example, you'll see that they're fairly straightforward. So let's say your object is made up of multiple point objects that have a certain mass and are located at different x and y values. Then you find the x coordinate of the center of mass by computing the following, and the y coordinate of the center of mass by computing this. And again, similar to the moment of inertia, let's say you have a continuous irregular object. In that case, these sums end up becoming integrals. And again, we won't be asking you to do these integrals, for this class, but we want you to be familiar with them. So let's apply this to an example. So